Good morning, everybody. All right, where were we? Oh, I just have my coffee brewing in the background, which I am in desperate need of. All right, so get up the chat. All right, give me just a second. Go and grab my coffee. This is like peek into the life of Dr. Crook. Normally I've had this going already by now, but that storm kind of kicked my ass this morning. So it took a lot longer to get in than normal. All right. And out. Okay, so we ended up yum. Actually, yeah, that's where we ended up. Okay, so we were calculating recombination frequency, and recombination frequency in percent equals distance in centimorgans, named after Thomas Hunt Morgan, the father of genetics, essentially. Oh, yeah, it's better. All right, so, oh, hang on a second. Got to wipe something off the board. So essentially, we can do a whole bunch of these, right? Pick a number of different genes, which we think are on the same chromosome or we suspect are on the same chromosome, and do a bunch of different two-point crosses between the two genes. And from that, we can work out kind of where they are relative to each other. Okay, so there's a little bit of a kind of a work through here. I want to get through this and then we'll start three-point crosses, which are a little hairier. And where are we at the timetable schedule? Should check this before class, but I don't have time. Yeah, so we get on to DNA structure on Friday. So if we can finish three-point crosses today, that'll be awesome. If not, we'll finish them up on Friday. So essentially 50% recombination frequency equals 50% recombinance and 50% parentals. Now, if you have an equal number of recombinants and parentals, how often is recombination occurring between those two genes? Question to the class. Because recombination frequency can never be 100% because you always have the unrecombinable chromatids on the outside, right? If you remember, we've got the crossover, these ones on the outside will never recombine, they'll always be parental. So if we have 50% recombinants and 50% parentals, how frequently is recombination occurring between those two genes? Questions to the class. Have a think. So give me time to drink my coffee. So essentially, because there's kind of stunning silence there, it will look like, that's actually not the one I want. Do that one. So you should get a 1:1:1:1 ratio of the different allele combinations. Anybody? So the question was, how often, in terms of every meiosis, every 2 meiosis, whatever, how often must recombination occur to get 50% recombinance? I'll type it up. Or how often is recombination occurring if you get percent recombinance and 50% parentals? Oh. So essentially, recombination has to be occurring every single meiosis, right, between those 2 genes. So recombination is occurring all of the time between the sister chromatids, or non-sister chromatids, sorry. And it can never occur between the ones on the outside because they're not in contact with each other, right? So the homologous chromosomes pair up, cross over, and it's the non-sister chromatids next to each other that undergo recombination. The ones on the outside, these ones, periphery, do not. So if you get 50% recombination frequency, you can't get any higher than that because the ones on the outside can't recombine. That's essentially saying every single time that a cell goes through meiosis, you will have recombination between those 2 genes, right? And so if recombination is occurring all the time, every time between those 2 genes, are those 2 genes linked or not? They're not linked. Exactly, they are assorting independently. So when you take that bit of knowledge and you apply it to this, what does that tell you about gene A and all the others? If they're linked or not, yeah, but what does the number next to, if you do a cross between A and B, you get 50% recombination frequency. A and C, you get 50%. A and D, you get 50%. Is A linked to B, C, or D? No. Okay, awesome. So if you were trying to figure out a map, right, for these genes, ooh, my legs. Yeah, let's make sure you can see what I'm writing. It would look something like this. We're not making any assumptions whatsoever, Stephanie. Not one. And I'll show you why in a second. Right. So this is more than 50 centimorgans. That big M. Or more than or equal to. Right. We can't tell how far apart they are, only that it's far enough apart that recombination will always occur. Okay, does that make sense? Because once you get over 50, you can't get any higher than 50. So it's like if your speedo stops at 60. So hang on, let me type that down. So if recombination frequency is 50%, it can't be greater than 50%. Because that's just physically not possible, right? Because of those outer chromatids that can't recombine. Then two genes are not linked, but you can't tell how far apart they are. Pardon me. Only that they are at least 50 centimorgans apart. It's like if your speedo stops at 60, right? And it's pegged at 60, you don't know how fast you're actually going. You could be going 60, you could be going 70, you could be going 80. Right? Obviously, if you got like, cars looking like they're standing in the dust as you go past them, it's probably more than 60. But you can't tell exactly how much faster, and that's the same deal here. So we know that the A and the others are at least 50 centimorgans apart. So this, however, is a question, and you brought up a very good point, Stephanie, that you can never make any assumptions about gene order. You will only work them out empirically from the data that you have. Right, so if I use A, B, C, D as no relevance to what order they're in, even if I give you a gene order, right, just because I have to write it down in one order or another, doesn't mean that that is the correct one. You have to work it out from the data. That's especially important for 3-point crosses, which we'll get into in a bit. Okay, so which two genes are the closest together? Looking at that list. If 50%, yes, cool, that was fast. B and D, right? 10 centimorgans apart. So already, this doesn't look right, does it? So we have B and D at 10. Hang on, let me, yeah, I'll just have to rely on you for the numbers because this will make it a little bit easier for everybody to see. Okay, what are the next two closest together? I can't actually tell because I can't see it right now. I'd have to get out of this. All right, what's the next smallest number, essentially? Oh, yeah. Oh, of course. Yeah. There you go. I'm sorry. I thought you'd still be able to see it even if I can't. Obviously, you can't. All right. Yeah, there you go. All right, C and D. So let's make that about like so, because they are directly proportional. So can C be between B and D? Well, B and C, actually. B. I'm sorry, got it the wrong way around. So B and C are 20, B and D are 10. Oh yeah, no worries. I was looking, I was like, oh, that doesn't make no sense. Thought I did it wrong. Anyway, so can C be between B and D? Given the numbers that we have. So if C were between B and D, Isaiah, B and C would be a smaller number. So if it looked like that, get a little bit closer. That's okay. So now you can double check the math and say, okay, well, what's the difference between C and D? it should equal the distance between these two and these two. Distance is 30. And so that makes sense, right? So here you can see clearly, right? The letter order before that was given was not correct. I mean, you can never assume that it is. Now, here's a question. Can you be sure that it's A, C, B, D? Why not? You're correct. Yeah, exactly. It could be the other way around because you have no information from A as to which of these two genes is closest to it because none of them are linked. That kind of gets to that whole more than 50 centimorgans apart, right? You don't know how much more. So essentially you have two possible maps. That's a D, not P. Could be that or that, right? How would you tell? What's the way that you could figure that out, potentially? Give you a clue. There's big open space here. More genes, exactly. You'd need a, what would that be, a fifth gene or even more potentially. That would be somewhere in between and linked to both A and to kind of these group, right? And so then you could say, well, from A to E is this, I don't know, let's say like 30. And then from E to D, if that number is smaller than from E to C, then it tells you that this is the correct order. If E to C, the number is smaller than from E to D, that tells you this is the correct order. And that's essentially what the people that mapped, like Thomas Hunt Morgan, Paul Sturdivant, I think his name was, if I pronounce it correctly. That's what they did when they mapped the chromosomes of Drosophila. Right, you find two close together, like white and yellow, for example. Then you find another one and another one and another one. You build up this physical map, well, linkage map, actually. And from that, you can work out essentially where genes are in a chromosome. And that will give you, let me just go all the way back to the beginning. Something that looks like this, right? And the number along the side, on the left side of the salamander thing, the chromosome, that is distance, linkage distance in centimorgans. And so someone worked all of this out, presumably by doing a whole ton of crosses. I mean, actually, you could take a shortcut and just sequence the whole thing. But this was the way that one would do it back in the day. Okay, does that make sense, everybody? We got how you can use map distance. Oh, and here's an actual kind of another one to work out. But we're not going to go into that. You can use that as a practice, see if you can get the same answer. What we're going to do now is spend some time on 3-point crosses. So essentially, the issue here is that you can have more than one crossover event between two genes, right? And if you do, then you end up with something that is a recombinant chromosome, but not recombinant for the two things you're looking at. So for example, if you look at, let's kind of blow this up a bit. Move this a little bit. Where? There we go. That's better. So if you have two genes that are fair distance apart and you do a 2-point cross with them, then there's a risk that you'll get a double crossover between, right? So you'll cross over from one chromatid to the other and then essentially cross back. So you'll swap out the bit between them, but the actual genes, essentially the bit either side, stays kind of essentially in the same combination. So even though these two chromatids are recombinant chromatids, right? They are a mix of the two parental chromosomes. They are not recombinant for A and B. The allele combination is the same. And so that's a big problem because essentially these are actually they should be used to work out genetic distance. But because you can't see them, you can't calculate them essentially, right? You can't work out how much they contribute to that. And so essentially what you end up with is a underestimation of recombination frequency and therefore distance, right? And so physical distance and genetic distance kind of get unlinked, right? They don't work so well. And again, this is simply because recombination frequency is what you observe, right? So if things go on which you cannot see, and those things are occurring between your two genes, you'll underestimate how much recombination is actually going on. So how do we get around that? Because obviously we do. The way to fix that is to use 3 genes at the same time. So the big plus of this is that it will detect those double crossovers. And also it means that you have to do fewer crosses, right? Because if you do 3 genes per cross instead of 2, you know, essentially you can work out gene order for 3 genes with 1 cross instead of 3 crosses, right? So it just takes a lot less time. So it's much more efficient as well. And so essentially, this is what it looks like, right? This is a little bit of a scary picture. So I'm just going to take a picture of the board, let you have a look at that first. Battery's back on my camera. All right, back in a second. Okay. So essentially, with a 3-point cross, there are 4 potential outcomes. You know, actually, now, you know what? I'm just going to draw this because I hate working off the PowerPoint slides. There we go. Yeah. Right. Obviously, when I do this in person, I don't have to carry a laptop around, which makes life a little easier. But then you don't get such a wonderful close-up view of me. Who wouldn't want that? Okay, so your 2 homologous chromosomes. And I'm going to use pluses and letters because it will hopefully kind of keep things a little simpler. What did I say I was going to do? There you go. All right, so just simple letters, something easy to write and hopefully understand. So essentially, you are going to get 4 potential outcomes from this. So you'll get 1, which will be parentals, or if recombination occurs, say here, right, and not between these, because these are close enough that it doesn't always occur. So say recombination occurs here or here, you will get essentially the same combination of alleles, right? Again, this is about what we can observe. So even if recombination does occur here or over there, right, you're not going to see it. You're going to get exactly the same combination of alleles. So you'll get that, and that. Plus, 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 plus. A, B, C, A, B, and C. Right? So that's parentals, non-recombinants. I'm going to short that into my kind of bastardized shorthand because it just makes it a lot easier to write. Then we have 3 potential outcomes of recombination, right? Depending on where recombination occurs between A and C and how many times it occurs between A and C. And stop me if it doesn't make sense. I'll try and move slowly so I don't get dizzy. So we have a single crossover between A and B, right? So I always tell people, and I do this myself as well, I'm not kind of pandering or, you know, being silly, but you just use your finger, right? So we're still going to get the parentals. Right, because they are chromatids that never undergo recombination because on the outside, right, they physically can't. And then if it's between A and B, right, we're going to go along here, past the first one, and then we're going to cross over to the other chromosome, right? So it's going to go like so with the plus, and then we're going to have BC. And this is important because you need to figure out what are the double crossovers and what are the single crossovers and what the gene order is. Okay, and I'll go through my patented 3 or 4 or 5 step plan in a little bit. So if you have this one, you've got to have the opposite, the reciprocal. Right, so it's going to go and include A, and then you'll get that. And so essentially, that's what you get for one crossover between A and B, right? So as if the crossover was here. Does that make sense, everybody? Cool. This is why I like doing it on the board, because I can take my time a little bit better. Yeah, that's kind of messy. Now, you can also have a single crossover between B and C. Again, this is all just random chance, right? This is, this one, well, we're not, I mean, how would you put it? So in the first one, It's simply the recombination has occurred outside of the things that we're looking at. And so because you'll end up with the same combination of alleles, you can't see that recombination occurring. Right? It's not so much that they're linked, like they're so close together that recombination cannot occur. It's simply that recombination occurred somewhere else on the chromosome and you didn't see it. So essentially this is just one possibility, right? So there are 4 different possibilities. One of them is this one, right? And that's pretty much always the case for any kind of cross. And really, in many ways, you don't care about that because it's nothing that's going to help you calculate recombination frequency. I just wanted to put it up there to kind of, I don't know, confuse you, maybe? I don't know. Try and make it clearer, but sometimes that doesn't quite work out. So you got a single crossover between B and C, right? So essentially that gives you, again, and kind of hammer home that point because it's an important one. Parental chromosomes, because you'll always get them. Again, that kind of comes back to the whole 50% recombination frequency equals unlinked deal, because you'll always get at least 50% of, well, 50% or more parentals, depending on whether they're linked or not. Now, recombination's occurring here. So you go along, we got plus plus, and then C. Plus plus, C. And the reciprocal, right? You'll always have the opposites. So that'll be AB plus. So far, so simple, right? However, this is the rub, right? As Shakespeare would say. You can also get a double crossover event. Now, these are much rarer because remember how we talked about probability, right? So if you have, essentially, these are independent events, right? Whether you get recombination here or here is independent, right? Equal probability. What do you do when you work out the probability of 2 independent events occurring? It times them together, right? It's like, you know, if you play roulette, got X chance of winning on the first round, X chance of winning on the second round, right? What's the chance of you winning twice in a row? Well, it's much lower than winning just once, right? It's kind of like the way I like to think. And gambling is actually a pretty good way of explaining probability. Okay, so again, plus, 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 A, B, C. Ooh, make sure I'm pointing in the right direction. Now you're going to get plus from the first chromosome, going to cross over to this one, have B, and then going to cross back and have a plus. So the allele in the middle, and this is very important, moves. The ones on either side do not. I mean, they kind of do, obviously, but functionally they don't. So come along, we've got plus, B, plus, and the opposite, A plus C. So given what I just told you about, you know, just basic probability, right? Which of those 3, oh, hang on, didn't write that up. Which of these 3 possible recombination events or recombinant chromosomes is going to be the rarest? Which will you see least frequently, independent of how far apart those genes are? just as a basic probability deal, which would be the rarest? Think again about probability. If you flip coin twice, is the probability of getting 2 heads greater or less than getting 1 head if you flip it once? Flip a coin once and it's what, 50-50, one hopes, right? So 50% probability. What's the probability if you flip of getting 2 heads if you flip a coin twice? It's going to be a half times a half, it's a quarter, so it's going to be less, right? So double crossover events are always the rarest. That is very important. Okay, I'm going to leave that up while I take a picture. While I do, have a think about that, ask any questions. I'll move my coffee mug out of the way. Who has questions? Because we're going to do one. So I want to make sure you understand that before we do. I actually really enjoy doing 3-point crosses. It's like a fun little puzzle. I'm absolutely crap at crosswords, but 3-point crosses, fabulous. Oh, should have left that up. Okay. Mad evil cackle. Pen that's run out. Should have thrown it away last time. 3-point cross practice. Also known as, I gotta call myself Dr. Matt. I always think of Dr. Nick out of The Simpsons. Hey, I'm Dr. Nick. Dr. Matt's patented plan for 3-point cross success. Which we might get through today. If not, we'll continue the plan Friday. Yeah, Friday. Okay, so this is something you'll get in the exam, guaranteed. Promise you, you will get a 3-point cross question, or 2, or 3. So, I'm going to use the same letters, just because it means I don't have to think. All right. crazy time. Let's get some numbers going. I'm going to keep this one relatively simple with a twist. So, and this is not always going to be written in the same order, like in terms of grouping, but I'll always group the reciprocals together because I think that's just, yeah, cruel and unusual otherwise. So, okay. So these would be the data. So first step, right? And so essentially this is the result of doing 1 3-point cross. You're going to have 8 different combinations, essentially 4 groups. So the first step figure out the groups, right? This is relatively straightforward, relatively. So essentially, if we have a linkage, right, because otherwise we wouldn't be doing 3-point cross, which of these groups are going to be the parentals? If you remember the golden rule of linkage, linkage equals what? With regards to parentals, it's a something of parentals. An excess, correct. No, they're not all parentals because this is 3-point cross. An excess of parentals. So these are your parentals. Okay, so that's one group. Hey, actually, I've got like 3 different colors here. Next group. This is going to be single crossover. There's going to be a single crossover between A and B. This is where it gets a little complicated. Now, if we have 3 genes, A, B, C, the other one has to be between B and C. Right? And the most important one of all, which ones are the result of a double crossover? It's kind of a clue. It's going to be the last group that I encircled, right? So you're looking at numbers, Stephanie. Another way of doing it and these are, okay, good question. So the parentals are going to be the ones that you see most commonly, right? Because these 3 genes are linked, right? So you would expect linkage, well, recombinations not always occur, so you get more parentals, right? That's the whole deal. Now, which is going to be the rarest event? Thinking back to the laws of probability and independent events. The double crossover, right? So this is another way you can do it too. Which group here has the fewest. Yeah, the third group, exactly. Oh, don't want that color. So this group has to be the double crossover, because it is always, always, always the rarest, or the one with the fewest individuals. Just basic probability, nothing more than that, right? Because you have to have two independent events occur to see that combination. Okay? So really, this is, and find the double crossovers. Right. That's the first step. We can worry about these at another time. It's probably an easier way. This is actually how I normally teach. I don't know why I did it differently this time. Does that make sense? Anybody got any questions? Ask now. And I'll just add. These are the rarest equals smallest numbers. Oh, I'm sorry, Stephanie. That is just me being crap. Sorry about that. It's my job to not confuse you, right? I'm sorry. Thank you for double checking me, though. That always helps. No, that is right. Now you got me doubting myself now, Stephanie. Yeah, I think all the rest are right. Yeah. Yeah. Sorry about that, everybody. No excuse. Just make mistakes sometimes. Okay, so that's the first step, and that's arguably the most important step because the double crossovers tell you the gene order. Let me write that out. Right, and that's really important because you cannot trust me that I've given you the correct order in the data. You have to work it out every time from the data. And so the double crossovers, and this is where things get a little bit confusing. And so don't stress too much if you are confused, because we'll continue this on Friday. The double crossovers are where the middle allele moves. And so essentially what you're looking for is in this group, which allele has moved. Questions to the class. Got 1 minute left. Look at the parentals, which you need to know to figure this out. We've got plus, 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 or ABC. Look at the double crossovers. Which letter has moved? The C. So if the set, thank you, Brianna. So if the C is moved, that one has to be in the middle. So the correct gene order is A, C, B, or B, C, A. Doesn't actually matter which way around. All right. Now that I've traumatized you enough, I'm going to leave it there. We'll continue on Friday. Okay, have a cogitate over that. Read through the PowerPoint and then we'll continue this and I'll actually continue working through this. I'll take a picture so I remember what I'm doing. Cool. All right, I'm going to leave that up for a little bit while I take a picture. The thing, Caitlin, is that you're right, it is tough, without a doubt. Practice always helps. But if you follow what because I've taught this a lot of times, right? And generally speaking, like this is a way that helps. Oh, before anything, Yadira, do you want me to remove that number before posting the chat, or are you happy for it to stay there? Need to let me, otherwise I'll take it out before posting it, just because that will be kind of public for the class. Okay, cool, thanks. So as long as you follow this kind of step by step plan, it will work. Guaranteed every time, right? It's like how you do chi-square crosses, stuff like that, right? You just have to kind of follow through the steps. And the way that I teach it is hopefully trying to take you through those steps one by one in a way that makes it a little simpler to do. And really, once you've done the first few, 2 or 3, it becomes fairly straightforward, right? You just have to follow the steps. Okay, we'll continue this on Friday. Yeah, practice always makes perfect with this stuff, right? Because, I mean, in terms of math, this isn't difficult, right? You just have to get your head around what's going on. Cool. All right, everybody. I shall see you on Friday or in an hour or so. Okay.